Okay, so parametric functions. If we have x and y, where they are both functions of another variable, so usually we use t, but you could use any variable you wanted to. Sometimes we're going to look at some polar functions as a function of theta as parametrics. But usually we'll talk about parametric functions as x equals something in terms of t with y equals something in terms of t. And then perhaps we'll give some restriction on the values of t. So t might only be greater than or equal to 0, or t might be all real numbers, or t might only go from -2 to 2. And so we only graph the pieces of the x values being from 0 to infinity and the y values being from 0 to infinity, but we still just plot them on a regular xy plane. So let's just start off doing this really quickly by plotting some very simple basic points. We know that we're starting at t equals 0 because t is only greater than or equal to 0. So if t equals 0, that's definitely an L, not a t. If t equals 0, what ordered xy pair do we get? X is root 0, which is 0, and y is 0. Easy enough?
Yep.
Perfect. What about when t is 1? What ordered pair do we get?
1, 1.
1, 1. It's like you can do basic arithmetic. All right, what about when t equals 2? We ought to get root 2 comma 2, which root 2 is like what, 1.4 or something? And let's see, we'll skip 3. How about t equals 4? That one makes better sense. What do we get?
2, 4.
2, 4. Yeah, don't fight over who's going to say it. And what about t equals 9? It's all very exciting, right?
3, 9.
Yeah, look at that. You can square root. That's good. All right, and so on. We can see what's going on here. What's going on here? What do we have? We have half of, oh, that was terrible. Half of a parabola, right? We just have the right half of the parabola y equals x squared. So let's see if we could have taken our parametric and converted it into a regular rectangular Cartesian equation. So what do we know about x and y? Well, they're both related according to t. So if I know what, let's say, y is in terms of t, or what t is in terms of y, I could take that and plug it in for the x value, right? X equals root y, or effectively x squared is equal to y, or y equals x squared. Now, what about the piece of this that's on the left-hand side that we didn't draw?
Who cares?
That's right, who cares? Because we're only interested when t is greater than or equal to 0, which gives us what restriction? Right? If t is always positive, right, and we're having an x value that's always the square root of that number, well, starting at 0 to infinity, what are our x values only going to be? They're only going to be positive values, because we can't take a square root and get a negative number, right? So that's just based on the restriction that x has to equal root t. So it's y equals x squared for x greater than or equal to 0. Good or no?
Yes.
All right. The parametric functions don't get a whole lot more difficult than that. We're going to start off with this really fun and exciting trig one. X equals 2 cosine t and y equals 2 sine t. Any thoughts on what this should look like?
Some kind of circle thing.
Some kind of circle thing. Yeah, there's going to be some kind of circle thing. So how are we going to prove that this is some kind of circle thing? Because plotting a bunch of points is going to be a little bit of a pain. And it's a lot of trig functions to evaluate and points to plot, and I don't want to do that. So let's see if we can turn this parametric into a rectangular, and then we can sort of develop a rule for it. So how are we going to turn this into a rectangular equation?
Square x and y, so you get x squared and y squared.
All right, I got x squared equals what, 4 cosine squared t, and y squared equals 4 sine squared t. That seems fine. And then why did we do that? What are we going to do with that?
Cosine
You
squared
can
plus sine
just
squared
add
equals 1.
those two together.
Yeah, add them together. So that's going to give us the x squared plus y squared, and then I don't know who else it was that was getting half talked over there, but you're also right. All right, x squared plus y squared equals 4 cosine squared plus 4 sine squared. So added the lefts together, added the rights together. And then, yeah, somebody was saying that sine squared plus cosine squared equals 1. So we've got x squared plus y squared equals, well, if I take the 4 out, that's 4 times cosine squared plus sine squared, right? Or x squared plus y squared equals 4 times 1. Everybody good there? We know that this is just a circle, right? And centered at the origin has a radius of 2. Real quickly here, because you all know how much I love to go into Desmos and graph things. I'm going to show you how to graph a parametric in Desmos, just in case you ever need to do that for anything. So first thing, you're not going to actually type in x equals 2 cosine t. You're just going to write it as an ordered pair. So you're going to do parentheses, and then 2 cosine t, and then another comma there, 2 sine t, and close your parentheses. And then it's going to give you, when it does that, it's recognizing that you're trying to do this as a parametric, so our x value and our y value. And then you just need to change your restrictions to whatever you want them to be. There's 0 to 2 pi. So it's just our circle with a radius of 2. Everybody good with that?
So it shows the portion of the circle that you like give the amount of radians of.
Exactly. If I just said 0 to pi, it'll just show me from 0 to pi. Right. If I say 4 pi, well, then it's gonna, you can't see it, but it's going around here twice, right? If I want to know just from 0 to 1 radian, let's say, and there it is. That's from 0 to 1 radian. Yeah, that's exactly what it would be. If we went back to the previous one, what is that? Square root of t and t. And we had just 0 to infinity. You can't do 0 to infinity, but you can just put in some big number. I don't think it accepts infinity. Actually, I don't know. I don't believe it does. Oh, maybe it does. Nah, it doesn't. Lame. So I just put in some big number and it'll sketch it for you. So that was our first one that we did. Everybody good there?
Yes.
Cool. All right. Let's go on to the next one. So anytime you have x equals 2 cosine t and 2 sine t, or 3 cosine t and 3 sine t, or 8 cosine t and 8 sine t. In fact, I should have just kept it up here. Now I'm going to go back to it. Let's go 3 cosine t, 3 sine t, from 0 to 2 pi. You can see it's just a circle with whatever that coefficient was for your radius. So if I change this, to 5 and 5, we're going to have a circle with a radius of 5, right? So anytime that the coefficients on both of them are the same, it will give you a circle. And you'll note that if I flip these around, right, we still get the same thing. But it's not the same portion of the circle depending on our restriction. So like 0 to pi over 2 just gives us this part, right? Whereas 0 to pi gives us this part, and if I put the 2 pi, I get the full thing. But we got to recognize that this is starting and going in potentially a different direction, which is going to matter later on, but not right now. Everybody good with that?
Oh yeah.
All right. Wonderful. So, like I said, let's go on to the next one. Here we have 3 cosine t for x and 4 sine t for y. What do we think this is going to look like? You probably can guess because you probably noted what happens if I have different coefficients a little bit ago. I was going between the 3 and 5.
An ellipse.
That's right. This is going to be an ellipse. So let's go back and look at it. So I guess I shouldn't have deleted all that. 3 cosine t, comma 4 sine t from 0 to 2 pi. Just looks like an ellipse. It's an ellipse that the y value is going to go up to 4, and the x value is going to go over to 3. So the major axis is in the y direction and has a length of 8, and the minor axis is in the x direction and has a length of 6, so double these values. And if I made this a 5 sine t, it's just going to get a little bit taller. 6 sine t, it's going to get a little taller. Make this narrower, and you can do any of that. Or if you flip it around and turn this into a 2, let's say, then your major axis is now in the x direction, whichever one is larger is your major axis, and your minor axis is in the y direction. Everybody good conceptually with looking at those? I hope. All right. So the question is, how do we convert that into a Cartesian equation? Any ideas on that?
For the x, divide by 3 on both sides, and for y, divide by 4 on both sides, and then square it, and then set it equal to 1, like x squared plus y squared. Well, kind of.
Yeah, okay, so let me catch up with what you said. X squared over 9 equals cosine squared t, y squared over 16 equals sine squared t, right? And then similar to what we did before, add them together. X squared over 9 plus y squared over 16 equals cosine squared t plus sine squared t, or x squared over 9 plus y squared over 16 equals cosine squared plus sine squared equals 1. And so if you're not familiar with the standard form of an ellipse in Cartesian coordinates, you should be. Your major axis is just whichever one has the larger denominator. So our major axis is half of 16, or 8 in the y direction, and our minor axis is half of, sorry, not half of, but the twice the square root of this, which is 8, and twice the square root of this, which is 6, is the minor axis in the x direction. Everybody good with that or no?
Hi. Yes.
Okay. And so I got, just in case you wanted to take a look at it, that is the standard form for the ellipse in Cartesian, and all of the important major minor axes stuff that you should know about it. So I'll give you a second to write that down if you want to, and then we'll move on. Y'all good? Or anybody need a little bit more time to write that down?
Can we have another second?
Yeah. I'm in no hurry. I mean, except that I am. Everybody good?
Yes.
Is there a typo somewhere there or no? Because for the second one, you say that both the major axis and minor axis have length of 2b.
Yeah, there is a typo there. Let's see. If b is greater than a, yeah, then it should have a minor axis. Huh. Thank you for catching that, 2a. Oops. Not sure how I managed to do that. Okay, everybody good now? All right, what do you think about this one? 3 secant t for x and y equals 2 tangent t. Let's see if we can convert it into a Cartesian equation first, and then from there we should be able, if you know things you're supposed to know, you should be able to figure out what this is. So we're going to use the same concept, same process as we did previously. We're going to divide by the 3 and then square. So I'm going to say x squared over 9 equals secant squared t. And I'm going to say y squared over 4 equals tangent squared t. And how are we going to want to combine these two things together?
You subtract the secant squared from the tangent squared.
I think you want it the other way around. But yeah, right idea. 1 plus tangent squared equals secant squared, right? So we want to subtract the tangent squared one from the secant squared one. I think you said the opposite way, but right. Everybody remember this Pythagorean trig identity? Yeah, hopefully. So we want a secant squared minus a tangent squared, which ought to give us 1. So we'll say that x squared over 9 minus y squared over 4 equals secant squared t minus tangent squared t. Or x squared over 9 minus y squared over 4 is equal to 1. And what is that the equation of?
Hyperbola?
That's right, that is a hyperbola. So let's real quickly take a look on the graph. What do we have? We have 3 secant t, I think, right? And 2 tangent t. And 0 to 1 is no good. We'll do 0 to 2 pi. There is our hyperbola. Right? And know that these hyperbolas have oblique asymptotes here. And there's a line along here that they are approaching but not touching on both sides. It makes like an X through the middle of it, through the origin. So there is our hyperbola. If I make this, let's say 5, it just flattens it out more. Let's say I make this 7, it's going to widen it out more. And we can flip it. Oh, I just can't see it because my coefficients are too big. There we go. We can flip it the other direction by flipping the tangent and the secant around. All right, so we can get it so that it's opening up and down rather than opening right and left. Everybody good there? Yeah?
Yes.
Okay. And just in case you want to know the Cartesian stuff for it, they're the standard forms for horizontally and vertically opening hyperbola. And then how you find out. Yeah.
Wait, can you go back for a second, please?
The Desmos or to the previous page?
The previous page.
Sure.
Okay, thank you.
Yep. All right. So like I was saying, these are the standard forms for the horizontally and vertically opening hyperbola. right? X squared over a squared minus y squared over b squared if it's going to open horizontally, and y squared minus the x squared if it's going to open vertically. And it's always the plus or minus the value underneath the y square rooted divided by the value underneath the x square rooted times x as your asymptotes. So you can always, should be able to remember that because that's the slope, right, of the line, and it's should be the y over the x, the change in y over the change in x should be your slope. So you can remember that it's the square root of the y over the square root of the x. Everybody good with those? No questions, no issues? You guys need a second to get that down or no?
Yeah, can you just leave that for a second?
Yeah. Just let me know when you all are ready and we'll move forward. We don't have a whole lot more with parametric to do, but get through it and then start some limits. All right, everybody good or no?
I think we're good.
All right. If you're not, leave a little space and notes will be up. I don't know what happened with yesterday's video of the lecture. I'm not sure why. When I went on this morning, it said it was only 91% uploaded. So I canceled it and restarted it. So it should be up there now. But for some reason, it didn't finish uploading yesterday and didn't post. So it should be there now if you were looking for it. All right. So graphing a parametric is extremely easy if both pieces of it, the x piece and the y piece, are both linear. So in this case, they're both linear. And if they're both linear, it means that the parametric itself will also just be linear. So if you can find the first point at t equals 0 and the last point at t equals 1, plot those 2 points and just connect them with a straight line. So if t is 0, what do we get?
0,2.
Perfect. And if t is equal to 1, what do we get?
4,1.
4,1. Yep. And so since this is a closed interval, they both have closed endpoints. And there is our straight line connecting the two of them. Easy enough. All right. You guys do this one real quickly on your own. It should be very straightforward. What was your first point?
-1, 4.
-1, 4. Good. I agree with that. And what was your last point there? Since they're both linear, we can just do the first and the last and connect them. Should have got what, 3,10. Let's see. And a nice easy line between there. Pretty straightforward. Let's practice one more of these where you need to write the parametric in a Cartesian form. This one's not quite as nice and easy as the ones we've seen before, but I'd like you to get it all the way solved down for y in a Cartesian equation. Any thoughts on how we're going to do that? Probably note that this one's a little bit different. Why is this one different than the ones we did previously?
There's a squared in front of one of them.
Yeah, one of our trig functions is already squared. Like the first one's not, but the second one already is. So we're going to have to find some way to use the Pythagorean trig identities to combine this all together, but it's going to be a little bit more difficult.
Could you divide both of them by 2 and then use 1 plus cotangent squared x is equal to cosecant squared x?
All right, so let's put on the side here 1 plus cotangent squared t is equal to cosecant squared t, and see if we can use that one. So if I divide by the 2 and square, that's going to become x squared over 4 equals cotangent squared t, which is great. This one is what? Y over 2 is equal to sine squared t. Well, how does that help us? What are we going to do with the sine squared t and the y over 2?
Can't we take the reciprocal of that one?
Sure, so that would give us 2 over y equals cosecant squared t. And then what do we need to do then? If we want to get 1 plus cotangent squared equals cosecant squared, to get 1, we ought to do cosecant squared minus cotangent squared. So 1 equals 2 over y minus x squared over 4. And then all you have to do is solve it for y, right? Should be pretty easy. Add the x squared over 4. And we'll probably want to get a common denominator on that. So make that 4 over 4. And then we're going to multiply by the y. And we'll then do the 2 divided by all of this stuff to just be left with y, right? Y equals 2 divided by, well, this was x squared plus 4 over 4. And so we'll take the reciprocal of that denominator and multiply it through to get y equals 8 over x squared plus 4. That should be a graph that you remember from last year with any luck. Anybody remember that graph? What it's called, what it looks like? No, nobody remembers.
It has the asymptotes, and I forget what the curves are actually called, but there's 2 of them.
It has the asymptotes, and you forgot what the curves are called. I don't know. It's got one horizontal asymptote, if that's what you're talking about. But this is specifically called the Witch of Agnesi. Yeah, nobody remembers that? The Witch of Agnesi? No. It's a very exciting graph.
I don't think you ever mentioned it.
Oh no, I must have. I think you are supposed to do it in like one of your quizzes or packets or something. It's not a big deal. It's not really all that exciting anyway.
It was quiz 0 last year.
Yeah, there you go. It was quiz 0 last year. See, somebody remembers. That's good. Anyway, this is what it looks like. It's a cool graph, I guess. And that's it. That's all for that one. Everybody good there? Any questions on that one? No? All right. Last thing we're going to do with parametrics here is we are going to see if we can find a parametrization for the line segment that has endpoints of -2, 1, and 3, 5. So I want you guys to take just a couple of seconds here and see if you can figure it out how to do this. Now, I'm not giving you a restriction on the t values. So you can choose what t value you want to start and end with. And depending on what you choose, you will end up with perhaps a different looking parametric equation than somebody else might end up with. And that's fine. If you want to do it the easiest way possible, then have your beginning endpoint be 0 and have your last endpoint be, t equals 1, or really any other number, but t equals 1 will make the arithmetic more simple. But you can do it with any set of 2 t values. So I want to see if you guys can figure this out. I'll give you guys about 2 or 3 minutes to try and figure that out, and then we'll talk about how to do it. All right, ready to go. All right, so let's talk about how we might have done this, starting with t equal to 0. If t was equal to 0, what does the x value need to equal?
X, t minus 2.
It needs to be, yeah, well, probably not an a. How about a times t minus 2, right? And we know that the t value is going to be 0, right? So that's just going to give us an x of -2. And what about our y value? We'll call that some other constant, b times t, then plus 1, because at t equals 0, that's going to give us this 1 value. Yeah? Everybody good there?
Yes.
All right. What about at t equals 1? Our x value should still be some a value times our t value, which is 1, and then minus 2, right? And our y value should be b times our t value, which is 1, plus that 1. And what should x equal? And what should y equal? X should be 3, and b should be
5.
Or sorry, y should be 5. And that's going to give us what? What are we going to do here?
We need to find the slope between the 2 lines, or the 2 points.
Okay, so if we, and what is finding the slope between those 2 points going to do for us?
Find a and b.
Okay. All right, so the a and the b, which are, how are we going to find those then? Just take these little equations and solve them, right? A minus 2 equals 3 and b plus 1 equals 5. And that ought to be good enough, I hope. Shouldn't have to be finding the slopes. A is 5 and b is 4, which tells us that we have x equals 5t minus 2, and y is equal to 4t plus 1. And this is for t is greater than or equal to 0, less than or equal to 1. And if you plug in t equals 0, you got to get -2, 1, which you do. And if you plug in t equals 1, you got to get 3 and 5. Everybody okay with that?
I have a question.
Yeah.
Are we supposed to always assume that we're trying to go from t equals 0 to t equals 1? Like, can it go from?
You will most likely, if you are asked to do this, which is unlikely, you'll probably be able to choose the value that you start and end at, and you'll want to use t equals 0 as one of them. If they specifically told you Yeah, I mean, let's say they specifically told you go from t equals 0 to t equals 5. Well, our process would be almost exactly the same, right? Except that over here at t equals 5, we'd have 5a minus our 2 equals 3 and 5b plus our 1 equals 5. But if I said we needed to start at t equals 1, let's say, and go to t equals 2, then we'd have a little bit more work to figure out, and we could have a lot of different answers. We'd have to pick some constants over here on these values. It could be -2 and +1, but it wouldn't have to be. We could pick, constants of 5 and 10, let's say, and we'd plug in an a or a t value of 1 and a t value of 1, and then we plug in our with the same constants, we'd plug in a t value of 2 and a t value of 2, and we'd have a system of equations that would need to be solved. Does that make sense?
So like usually on like a problem, they're gonna tell you the t's, like the t parameters. You're not gonna like decide on your own.
Yeah, if in the very, very, very small chance that this is something they actually ask you to do, yes, they will most likely give you the option of choosing your own.
Okay, got it.
Yeah, but the chances, I mean, we're just trying to get some of the basic ideas down right now for parametrics. The chances of you actually having to do this exactly on the AP test are very, very, very slim. So.
Okay, thank you.
Yep. All right. That is it for parametrics now. Luckily for all of you, we still have almost a full half an hour, which means we can get started on limits. So give me just 1 second here. So we're going to real quickly just talk about what a limit is and how to find simple limits. And we're going to sort of blaze through some pretty easy questions and try and get through as much stuff as we possibly can today with limits, so we have less to do later in the week. I may, depending on how much we get through today, give you guys your first assignment to complete that's going to have some limits questions on it today, but we'll see. We'll see how much we get through. All right. So everybody good and ready? Okay, good. So remember, when we talk about a limit is what happens as we get very, very close to this a value. It doesn't matter what happens at that a value. It just matters what happens as you get very, very close to it. And when we think about finding a limit, we ask ourselves these two questions right here. We ask ourselves, as x gets close to that a value, does the function approach some real number? And key point here, real number of L. Okay? And can we make the function get as close to that real number of L by choosing x values that are very, very close to a? If both of those are yes, then we say that this is true. And then we say the limit as x approaches a of f of x equals L. Okay? Everybody good with that? That's the basic idea behind the limit, right? Can we get as close to L as we want by picking values very, very close to A? That's the whole point of all of this. And graphically, it looks about like this. We've got some function that may or may not be defined at A. It's okay to have a hole there. And as we approach A from both sides, as long as we can get as close to L as we want, then the limit exists, right? And remember that it doesn't matter that A is not defined or A may be defined. It doesn't matter whether or not it is. All that matters is as we get close to it, do we approach that real number L? Everybody good with the basic idea of what a limit is? We're not going to do any further proofs of it. We're just going to practice some problems. So all good? Any questions, any issues? You are all still there? You can hear me?
Mm-hmm.
All right.
All right.
Yeah.
Wonderful. All right. If you have a continuous function, finding the limit is very easy. And whether the function is continuous or not, or whether you know if it's continuous or not, the first thing that you should always do with a limit is just plug in your a value every single time. If you get a real number out when you plug it in, then you need to just put that in a box and be done. If you don't, then you're going to have to do some extra work. So what should this first limit be? It should be plug in the 4, gives you 8 minus 3 or 5. Easy enough? I really hope you are all able to do that.
Yes.
You're in horribly the wrong class. All right. What about the limit as x approaches -3 of x squared plus 1? That ought to just be -3 squared plus 1 or 10. Easy?
Yep.
Yes.
Put in your 7, you end up with the square root of 7 plus 2. Square root of 9 is 3. Make sure you do 3, not plus or minus 3, right? The only time you get a plus or minus is if you're solving the equation. And there's no equation to solve here. We're just evaluating an expression that has a square root in it. All good? Perfect. Okay. Real easy. The limit as x approaches 1 of f of x. If f of x is x plus 2, what should it be?
Three.
It just be 3, plug it in. We'll note that that is the value of the function at x equals 1. Easy one. What if I gave you this one, though? X squared plus x minus 2 over x minus 1, where there's a hole at x equals 1.
Still 3.
Still 3, because we remember it doesn't matter what's happening as we approach as we get to x equals 1. It only matters what happens as we approach x equals 1. And we know that this could factor into x minus 1 and x plus 2. Pretend I actually wrote an x. There we go. And those x minus 1s cancel out. And you just have this x plus 2 function with a hole at 1. The hole doesn't affect anything. Even though g of 1 does not exist, the limit there still does exist. A hole doesn't stop the limit from existing. Everybody good there?
Yes.
All right. Here is our next one, h of x. It's exactly the same, except that when x equals 1, the value of the function is 2. What's the limit as x approaches 1 of h of x?
Still 3.
Still 3, right? It doesn't matter what happens at x equals 1, which is the function equals 2. All that matters is what happens as we approach x equals 1. We can still get as close to 3 as we possibly want by picking numbers very, very close to x equals 1. We can get to 2.999999999 as long as we pick something very, very close to x equals 1. Everybody good there? Okay, so we noted that for the first one, f of 1 was 3. For the second one, g of 1 did not exist. And for the last one, h of 1 was actually equal to 2. But the limit as x approached 1 of all 3 was still equal to 3. So you can have a case where the function and the limit have the same value. The limit exists, but the function does not exist there, or the limit and the function have different values. Everybody good? All good with that?
Yes.
Perfect. Okay. So how do we algebraically determine these limits? Well, one of the ways that we can do them when they are indeterminate, and right, remember what is an indeterminate limit? It's a limit that is 0 over 0, right? And when we have an indeterminate limit, one of the ways that we can solve them is by factoring and canceling stuff out, right? Y'all remember this, I hope. Those x minus 2's will cancel. This becomes the limit as x approaches 2 of x squared over 3, which is just 4/3. Right? Everybody remember that? One of the ways that we can do this.
Yes.
All right, cool. There's a lot of other ways, right? Well, at least one other good way for these, but we'll worry about that later. What's the limit as x approaches 2 of f of x of this function, for f of x being 2x squared minus 5x plus 2 over 5x squared minus 7x minus 6? Well, if you plug in 2, you end up with 0 over 0. So factor it out. You should be clued in that both the numerator and the denominator have a factor of x minus 2 if this comes out to be 0 over 0 as x approaches 2. And then you can just figure out what the other ones are pretty easily. Looks like 2x minus 1 and 5x plus 3. And we ought to be able to cancel out those x minus 2's, giving us this new limit, which should be 3 over 13. Good or no?
Good.
All right. What about this one? Should be 2 good ways to do this one without using tricks that we use things we haven't technically learned this year. What's one way to do this one?
Conjugate?
Yeah, after you've plugged it in and determined that it's 0 over 0, multiplying by the conjugate is one way. So we're going to say the limit as x approaches 9 of x minus 9 over root x minus 3. And we're going to multiply by the conjugate of the denominator, because that will clear out the radicals from the denominator and turn that denominator into what? Just that x minus 9, which will cancel. And now this new value here is root 9 plus 3, or just 6. Good or no?
Good.
What else could we have done? We could have taken the x minus 9 and said, oh, that's a difference of squares. Even though it doesn't look like our standard difference of squares, we could have said that ought to be root x plus 3 and root x minus 3. So doing some creative factoring can often help us out. Okay, the root x minus 3's will cancel, and we've just got root 9 plus 3 or 6. Either way is good. Obviously, you can also use L'Hopital's rule on it, but since we haven't yet talked about derivatives, I'm going to tell you not to do that quite yet. Good or no?
Good.
Perfect. All right, let's do another one. Here we have a complex fraction. How do we deal with the complex fractions? First thing is plug in the 1, right? And what does that give us? It gives us a half minus a half over 1 minus 1. So it gives us 0 over 0. It gives us indeterminate. So we got to deal with that in some way. What's the way we're going to deal with that?
should we distribute the x minus 1 to the denominators?
I mean, I guess we could, but that sounds like I'm making it look really ugly first. I mean, we're going to do that eventually, but let's combine the numerator together first, and then we can distribute that into it. So how can I combine the numerator together into one fraction? With a common denominator, right? Just like that, yeah? All over x minus 1. I'm just going to write the x minus 1 over 1 because sometimes that helps people to realize that all I'm really doing with that is taking it up here, taking the reciprocal, and then multiplying it. Right? So that x minus 1 ends up in the denominator. So we got a limit as x approaches 1 of 2 minus the quantity x plus 1. So 2 minus x minus 1 all over 2 x plus 1 x minus 1. Everybody good there or no? And if I combine the 2 and the minus 1, I get a 1 minus x in that numerator. And how can I now deal with this? Because it's still indeterminate, right? It's still a 0 in the numerator and a 0 in the denominator. In order to cancel some stuff out, I'm going to have to factor a negative out of either the numerator or the denominator. I'll just do it out of the numerator to give myself that x minus 1 term that I really want to cancel. Those will go away. And now this becomes negative 1 over 2 times 1 plus 1, or negative 1/4. Good or no?
Great.
All right, spectacular. Let's, I don't think I have one in here. I meant to put this in here. Let's do one more problem. Let's do this. The limit as x approaches 0 of the cube root of x plus about 27 minus 3 over 3x. Everybody good with that? First thing we should do is plug in that's right, plug in 0, and that gives you 0 over 0. And so now how are we going to deal with this one? Nobody remembers how to deal with this? Oh, man.
U substitution.
Yeah, thank you. We're going to do a u substitution. We're going to let u equal the cube root of x plus 27. Anytime you get these cube root expressions in here, best case is to do a u sub. And we're going to have to figure out not just what u is, but also what x is. So what's x? It's u cubed minus 27. And so if we're going to convert everything that was x's into u's, we also need to convert this x approaches 0. So as x approaches 0, u ought to approach the cube root of 27, or 3. So we can fully rewrite this as the limit as u approaches 3 of u minus 3 over 3 times u cubed minus 27. And obviously that is still indeterminate if we plug in 3. So we got to do some factoring. You should know how to factor a difference of cubes. U minus 3 times, it's supposed to be a square. That didn't really look like a square. That's better. U squared plus 3u plus 9. Cancel out your u minus 3's. And you've got the limit as u approaches 3 of 1 over 3 times u squared plus 3u plus 9. Everybody good with that? And just evaluate and get 180 first. Any issues, any problems, complaints, concerns, questions, queries? All good? Just some of these basic tricks for evaluating limits. Any questions so far? Promise we're almost done.
All good.
All right. So we should, with any luck, know that there are also left-hand limits and right-hand limits, and that the same rules will apply, except that in order to find a left-hand limit, all we have to have is an open interval to the left of A. And to find a right-hand limit, all we need is an open interval to the right of A. And we'll talk about this in a second, but we should know that in order for a two-sided limit to exist, the left-hand limit and the right-hand limit must be equal. They must both exist and they must be equal. Okay. So let's see if we can apply this to a nice simple function, f of x equals radical x minus 2. What's radical x minus 2? It just starts here at 2, 0 and looks about like that. Don't like crucify me if that's like not perfect. I'm sure it's not perfect, but it could be better, but it's not bad. What's the limit as x approaches 2 from the right of f of x? So I only have to have an open interval to the right of 2. As I approach 2 from the right, what do I get very close to?
0.
0. What about as I approach 2 from the left?
Does not exist.
Doesn't exist because there is no interval, open interval to the left of 2. And since there's no open interval surrounding the x equals 2, we can't have a two-sided limit either. Good or no? Hopefully.
Great.
Great. It should all be easy. And so like I said a minute ago, the two-sided limit equals L equals some number if and only if the left and the right hand limits both equal that same number. If they don't both equal that same number, then there is no two-sided limit. If they do both equal the same number, then for sure there is a two-sided limit and it is the same value. All right, so let's look at this one, the absolute value of x over x. Here's the graph. And we should very easily be able to just look at the graph and say what the limit as x approaches 0 from the left is. What is it?
-1.
-1. And as we approach 0 from the right, it should be
1.
+1, which tells us that the two-sided limit does not exist, right? Everybody should be okay with that, I hope. But what if I asked you to do this algebraically? So if I asked you to do this algebraically, you'd have to remember the definition of absolute value. So if I'm approaching 0 from the left, what could you tell me about every x value that is important to this limit? They are all, when I approach 0 from the left, all of the x values are
Negative.
negative. X is always less than 0. And if x is less than 0, the absolute value of x is
-x.
-x, or the opposite of x. And for the one from the right, x is greater than 0, if we're approaching 0 from the right, then the absolute value of x is just equal to x. So we could rewrite this as the limit as x approaches 0 from the left, not just of absolute value of x over x, but because the x values are negative, negative x over x, which gives us the limit as x approaches 0 from the left of -1. And the limit of a constant is always the constant. That one should be drilled into your memory forever. The limit of a constant is a constant. The limit of a constant is a constant. The limit of a constant is a constant, right? You should remember that. Everybody good there?
Yes.
Perfect. And so then what about this one? This one, since it's a limit as x approaches 0 from the right of f of x, should be the absolute value of x is just x, so it's x over x, which is the limit as x approaches 0 from the right of 1, which is 1. And still, the two-sided limit doesn't exist. All good or no? Okay.
Yes.
Cool. So we're going to do one, maybe 2 more pages, and then we're going to be done. We've got a piecewise function here. 3 minus x if x is less than 1. 4 if x equals 1. And x squared plus 1 if x is greater than 1. So as x approaches 1 from the left, which piece of this piecewise function should we be using? If we're approaching 1 from the left, that'd
3
be
minus x.
Yeah, that'd be when x is less than 1. So this is the limit as x approaches 1 from the left of 3 minus x, which is just 2. And what about as we approach 1 from the right? We should be using the x greater than 1 piece. So this is the limit as x approaches 1 from the right of x squared plus 1, which is
2.
also 2. And if the limit from the left is equal to the limit from the right, then the two-sided limit is also 2. It's the same value. And we could have graphed this. And if we graphed this, what do we end up with? 3 minus x for x less than 1. Oh, that was not anywhere close to that straight line. That was not horrible. There's 3 minus x. And then we had a point at x equals 1, x equals 4. And then we had a parabolic part going up on the other side. And we can see graphically that, yeah, from the left, it's approaching 2. And from the right, yeah, it's approaching 2, which means that the two-sided limit should be 2. It doesn't matter that the value of the function at x equals 1 is 4. All that matters is what happens as we approach x equals 1. Good?
Yes.
All right, last thing, which I already mentioned, the limit of a constant is the constant. All right, so the limit as x approaches a of c, that constant is c, that constant. The limit as x approaches 3 of 7 is 7. The limit as x approaches -4 of 10 is 10, which should make sense because all of these constants are just horizontal lines and the y values don't change. So tomorrow, we're going to talk about the other rules for limits, talk about the sandwich theorem, prove some other fun and exciting stuff, and with any luck, blow through almost the rest of all of our limits stuff. Good or not good?
Good.
Good. All right. Let's